Okay, so here's part 2 of chapter 11, and here we're talking about null effects. Okay, so this is different than internal validity threats. This is where you find a null result where the IV is not shown to have an effect. There's no, for example, maybe you give people money, a lot of money, a little bit of money, and no money, and you hypothesize that it's going to affect their happiness, but it actually doesn't change it. So a null effect, no difference between the groups. Okay. It may be the case that it's actually true, that the true state of the world is that the IV does not really have an effect. That's a valuable thing to know. Okay. If this is like a treatment that you're investigating or whatever, if it doesn't have an effect, then that's important to know because you probably shouldn't use it, and people shouldn't spend money to use it. And it could also be that the IV really does have an effect, but you just didn't find it with this particular study. It was not shown in these results. Okay? And statistically, this is going to happen sometimes. Like a 95% confidence interval, for example, if you calculate 95% confidence intervals multiple times, 5% of them are going to be shown to include 0, meaning that's a null effect, but that's just going to happen statistically. That's how they work. That's why they're called 95% confidence intervals. Okay. It could be that there's not enough between groups difference between the two, and here are some reasons why that could be the case. Okay. It could be that there are ceiling or floor effects. Ceiling effects meaning scores are clustered at the top. Floor effects, they're clustered at the bottom. Okay, so maybe an example is maybe you have some kind of a game or a quiz that you're having participants complete, and if it's too easy, then everybody gets all of them right, and you don't pick up on any differences between the groups. Okay, and if they're too hard, then everybody gets them wrong. Just note that this can be caused by issues with the independent variables, with the treatment itself, and also with what you're measuring. Okay? Or the treatment is too strong or too weak, or for example, the task is too easy or too hard. Okay? It's good practice then to include a manipulation check as part of your study. Okay, so if you have some manipulation that you expect will have some kind of an effect, like something that'll cause anxiety, then you'll want to verify that it does. Okay? Or if you're investigating the effect of humor on how well people remember what's taught in a college classroom, then you'll need to verify first that people actually find whatever class or whatever professor funny. So you'll want to have people rate the funniness. You should expect significant differences between like the high anxiety, medium anxiety, low anxiety group, indicating the manipulation does work, versus if you don't see any change in anxiety due to your manipulation, then it doesn't work. Okay, now this is not your primary dependent variable that you're actually interested in. This is just one as kind of a check to make sure that your experimental design is working. So it's not the primary DV of interest. It's kind of an additional DV that you add in just to make sure the experiment's running properly. Okay. Just so you know, we talk about confounds providing alternative explanations for differences that we observe, but sometimes we could say that design confounds kind of work in reverse and kind of erase differences that truly are there, but you can't see them because of design confounds. Okay? So just something to keep in mind. So if you're observing a null effect, you'll want to investigate if there are any potential confounds that could have led to the null effect, rather than assuming that internal validity is fine just because you didn't find any differences. Okay. Sometimes it's within groups variability. Okay, so we won't cover statistics in a whole lot of depth in this course, but variability is going to affect p-values and confidence intervals. Okay, so it's going to affect what you're actually looking at to determine if there is a statistically significant result. Okay, so measurement error, there's going to be some random noise in your measurement data. It's just always going to happen. More precise instruments will have less. less precise instruments will have more. It's always better if you can have a more precise instrument. Precision in your numbers, that's going to influence the p-value. Okay, so some variability in your data you can't avoid just because people are different and people behave differently. Human data is noisy, but you don't want to add extra variability if you can help it, just because your instrument, just because your tape measure is, for example, is wobbly, and so you can't get a very precise estimate, or your scale is getting jostled around by construction vehicles operating outside, and it messes with the measurements. Okay, if you can have more precision, it's better. And if you can't avoid an unreliable or a less precise instrument, then you may need to collect more people. Okay? There's kind of this inverse relationship between the number of the sample size and the amount of variability that you'll observe in something like a confidence interval. Okay? Or you can at least shrink a confidence interval where there's high variability by recruiting more subjects. Okay? Individual differences. If you just have a wide spread, then it's going to look like there's no difference, that there's no effect of receiving $1 on your mood, here in this fictitious example. So it may be better in that case to look at a within groups design. Okay, so that's where everybody functions as their own control and they're compared to themselves. And so here you can see that there is a reliable effect. Everybody goes up, even if it's just a little bit. Whereas you might not see that here if you're just comparing this average with this average. Okay. Again, a solution to issues with individual differences is to add more participants. Okay. There's an actual equation for calculating the 95% confidence interval, and a significant result, the confidence interval is not going to contain 0. Okay. So more narrow, you're more likely to miss 0, and so it's more likely to be significant. A 95% confidence interval is mathematically calculated. One of the terms in that equation is your n, okay, your sample size. So that's what you usually have the most control over. There's other components of the equation, the variability, and how much of a what your threshold is for statistical significance. Okay, but usually that's the primary thing that we have control over is the sample size. Okay. Now that can get expensive. It costs more money to do a bigger study, but if you can, then you may want to recruit more. Okay. Situation noise, we don't necessarily mean like sound noise, like high volume noise, but this is just any kind of external distraction that could cause variability. This is not necessarily an internal validity threat if you have, if there's stuff going on outside the lab that's distracting people, or, the lights are making noise, or there's just, there's weather patterns, or if people are doing a task but there's thunder outside, okay, that's an example of situation noise, any kind of external distraction. Okay? If it's not unsystematic, where you have about the same amount of external distraction in both your groups, then it's not an internal validity threat. But what it could do is lead to a higher likelihood of null results, because it's just going to introduce more variability and less precision. So you want to have a nice, tight, controlled environment as best you can. Now, sometimes that means you have to sacrifice some realism to minimize the noise, the situation noise. But sometimes that's what you need to do in order to see whether or not an effect is really there. And the other side of obscuring results is power. That's the ability to actually detect a true result. Okay? Likelihood that a study will yield a statistically significant result when the IV really has an effect. Okay? So your ability to catch a true effect that's actually there. The textbook doesn't really go into this, but this is something that you should do. It's best practice to do this before you even start a study, because you need to know how big of a sample size am I going to need to find an effect if it actually is there. So this is called the power analysis, and we won't go into the math behind it, but you can You can estimate based on what you anticipate the effect size will be, based on historical data and how big the variability is that you anticipate. You can say we probably need to recruit 500 participants in order to detect an effect if it's really there. Just a quick note that there's no results are kind of on the outside looking in, or they tend to be historically. They tended to be, but there's a push, and it's a good push to make null results more reported, to be reported more transparently. Null results they often seem less exciting. They're less glamorous, maybe less likely to be reported in the popular media. But they can be just as valuable and just as interesting as ones that actually show differences. Okay, showing that a therapy doesn't work is just as valuable as showing that a therapy does work, because then we're able to move on, and we can move on. We can explore what actually does. One example of a way to prevent this bias towards just publishing null results are called registered reports. That's where you, instead of conducting a study, getting the results, and then sending it off to a journal to get published, you first contact a journal and say, hey, I'm planning to conduct this study. I don't have my results yet, but here's my experimental design. This is the question I'm wanting to answer. Can you review my experimental design, make sure it's sound, and then once I conduct the study, I want to have it published. And if you register your report with a journal, then no matter what your result is, even if it's null, it'll get published. Okay. So anyway, that's the end of this section and the end of the chapter.